Quantum Computing Explained. Hey there, brilliant minds. Welcome to CHIZHIM SCIENCETECH YouTube channel, where we don't just explore science, we decode it. If you've ever wondered how a computer could one day solve problems too complex for even the most advanced supercomputers, you're in the right place. Today, we're diving into one of the most cutting-edge and transformative ideas in modern physics and technology, quantum computing. This is more than just faster processing. This is about unlocking the rules of the universe itself, by rewriting the way we compute reality. From particles that exist in two states at once, to machines that could one day break the encryption that secures the internet, we're going deep into the quantum world. Let's begin our journey into the future with the following points. Point 1. Classical computers, the foundation of the digital age. Before we can grasp quantum computing, we need to understand classical computing, the digital world we're all familiar with. Everything your laptop or phone does, from streaming videos to calculating equations, is based on bits, the smallest unit of data in classical computing. A bit can have only one of two values, 0 or 1. Think of bits like switches, off or on, black or white. Through billions of these bits operating in sync, classical computers perform complex operations. These bits are manipulated using logic gates, basic rules like and, or, not, which form the building blocks of modern processors. But here's the catch: as our need for computational power increases, classical systems are reaching their physical limits. We can only shrink transistors so far. We can only speed up processing so much. That's where quantum computing steps in, with an entirely new language. Point 2. What is a qubit? The quantum bit. Enter the qubit, short for quantum bit. Unlike classical bits, qubits don't just sit at 0 or 1. Thanks to the principles of quantum mechanics, a qubit can be 0, 1, or both at the same time. This phenomenon is called superposition. Imagine being in two places at once, or thinking yes and no simultaneously. That's what qubits do. But that's not all. Qubits are incredibly delicate. They exist in fragile quantum states that require precise environments, often cooled near absolute zero and shielded from even the tiniest disturbances. Qubits can be made from various physical systems. Trapped ions, where individual atoms are suspended using lasers. Superconducting circuits, tiny loops of current. Photons, particles of light traveling through fiber optics. Each type has its pros and cons, but all are designed to harness quantum properties for computation. The real magic, however, happens when we add superposition's twin sibling, entanglement. Point 3. Superposition, living in a multiverse of possibilities. In classical computing, if you flip a coin, it's either heads or tails. In quantum computing, that coin spins through the air, embodying both outcomes until you catch it. This is superposition, and it's not just a metaphor, it's real physics. When a qubit is in superposition, it holds a probability distribution between 0 and 1. Only when measured does it collapse into one value. Mathematically, we represent this using complex numbers on the Bloch sphere, a 3D space showing the infinite possible states a qubit can inhabit. With each additional qubit, the total number of states your system can represent doubles. 2 qubits equals 4 states. 3 qubits equals 8 states. 20 qubits equals over 1 million states simultaneously. This is where quantum computing begins to outpace classical systems. Point 4. Entanglement, the quantum connection. Now let's explore the second core principle of quantum computing, entanglement. When two qubits become entangled, their states are no longer independent. Changing one instantly changes the other, no matter how far apart they are. Einstein famously called it spooky action at a distance, and he wasn't exaggerating. In computing, entangled qubits can work together in ways that are impossible for classical bits. They share information and respond to operations collectively, enabling massively parallel calculations. Entanglement is what allows quantum computers to scale their power exponentially. Point 5. Quantum gates and circuits, rewriting logic. Classical logic gates use simple binary rules. Quantum logic gates, however, are unitary transformations, reversible operations that rotate qubit states in quantum space. Examples include Hadamard gate, H puts a qubit into superposition. Pauli X gate, equivalent to a NOT gate, flipping 0 to 1. CNOT, controlled knot entangles 2 qubits. T-gate, phase gate, apply complex phase shifts. Quantum gates are stacked into circuits that evolve the entire system state. Designing these circuits is like composing a quantum symphony, where timing, precision, and coherence are everything. Point 6. Quantum algorithms, solving the unsolvable. Quantum algorithms are not just faster, they are fundamentally different. Two of the most famous are CHIZHIM algorithm, 1994, can factor large numbers in polynomial time, threatening current cryptographic systems. Grover's algorithm speeds up database searches from linear time to square root time. Other groundbreaking algorithms include quantum Fourier transform, for signal processing. QAOA, quantum approximate optimization algorithm useful for combinatorial optimization in logistics and finance. VQE, variational quantum eigensolver, helps simulate molecular structures in chemistry. Each algorithm exploits quantum parallelism and interference to collapse onto the correct answer faster. Point 7. Real-world applications. Why quantum matters. So what can quantum computers actually do for the world? Medicine, simulating protein folding and chemical interactions with perfect accuracy. Finance, modeling chaotic market behavior or optimizing portfolios. Climate, simulating Earth's climate with greater precision. Artificial intelligence, enhancing machine learning models with faster matrix calculations. Security, enabling quantum cryptography that's theoretically unbreakable. Some applications may be 10 to 20 years away, but others are already being tested in early systems. Point 8. Quantum supremacy, crossing the threshold. In 2019, Google's 53-qubit Sycamore processor performed a random number generation task in 200 seconds that would take a classical supercomputer 10,000 years. This marked a milestone called quantum supremacy, the moment a quantum computer outperforms any classical system at a specific task. It wasn't useful yet, but it proved the potential was real. Other companies, IBM, Xanadu, IonQ, are pushing toward quantum advantage, where real-world tasks are solved faster, better, and more affordably. Point 9. The global quantum race, who's building the future? This is no longer just science, it's geopolitics. Governments and corporations worldwide are investing billions into quantum R&D. USA, IBM, Google, Microsoft, Amazon, Intel. China, quantum satellites and the Zhejiang photonic quantum computer. Europe, €1 billion quantum flagship program. Canada and Australia, leaders in photonic and silicon-based qubits. Startups like PsiQuantum, Rigetti, Xanadu, and D-Wave are driving innovation alongside giants. It's a race not just for computing power, but for scientific dominance. Point 10. The big challenges, what's holding us back? Despite the hype, quantum computing has serious hurdles. Decoherence, qubits lose their state fast, often in microseconds. Error rates, noise corrupts quantum information. Scalability, building from 50 to 1 million reliable qubits is no small feat. Error correction, quantum error correction requires thousands of physical qubits for each logical one. We're in the NISQ era, noisy intermediate-scale quantum, and full-scale quantum computers are still years away. But progress is accelerating. Point 11. Ethics and quantum security, a double-edged sword. Quantum computing's power raises serious ethical and security questions. Can it break all encryption? Yes, current RSA encryption would fall to CHIZHIM algorithm. Can we prepare? Yes, post-quantum cryptography is being developed now. Who controls the power? Governments? Tech companies? Militaries? Quantum technologies also enable quantum key distribution, a way to send unhackable data. But the question remains, will this be used for the public good, or controlled by the few? Point 12. The quantum future, where do we go from here? Quantum computing is more than a technology. It's a new lens through which we understand reality. Imagine modeling black holes or early universe conditions, designing life-saving drugs in seconds, breaking the barriers of machine intelligence. revolutionizing industries we haven't even invented yet. We're not there yet. But each breakthrough, each stable qubit, each new algorithm brings us closer. The next great leap in science won't come from a telescope, but from a quantum chip. Thanks for exploring the quantum universe with us. I am CHIZHIM SCIENCETECH. If you enjoyed this journey, hit like, smash subscribe, and tap the notification bell icon to stay tuned for more deep dives into the science shaping our future. Got a question about quantum computing? Drop it in the comments, and let's start a conversation. Until next time, keep questioning, keep learning, and keep expanding your reality.